All right, everyone, let's get started. Am I going to sing something? We could do karaoke after this if you want. All right. Our first speaker today is Brett Robbins. Brett received his BSEE and MSEE from the University of Illinois at Urbana-Champaign and is currently pursuing his PhD in electrical engineering. His research is focused on the distributed control and optimization of power systems. In addition to engineering, he has earned vocational certifications in automotive repair, refinishing, and welding. Brett.
Okay, thank you. Is this on? Okay. I kind of hear myself echoing a little bit. Okay, so for those of you that I have not run into yet, I'm Brett Robbins. I'm going to be talking about optimal tap settings for voltage regulation transformers in distribution networks. And I think this crowd in particular is very familiar with the push to integrate more technology into power systems, whether it be distribution systems, transmission systems, it could be renewables, it could be advanced control. And so the motivation for this work was we were looking at the volt-var problem using distributed energy resources, a very common topic. And then we're like, well, that would be considered more of fast transients. What about the slower stuff? What about the traditional hardware, such as transformers and capacitors? And so in distribution systems, it's common to utilize tap-changing transformers and switch capacitors in order to regulate voltage. And so a lot of times these devices are managed by automatic voltage regulators, which act based on local measurements. This could be either on the secondary side, it could be some sort of measurement on a local bus, a nearby bus. They could even be controlled manually. And so we're looking at this idea of controlling them manually and maybe doing the optimization elsewhere. And so this traditional approach with the decentralized approach to voltage regulation is effective for voltage control purposes, but it may not be optimal, especially in like, excuse me, system losses, flattening the voltage profile, or if you have some other performance criteria that you're trying to hit. And so what we're looking to do is we tailor the optimal power flow formulation for distribution networks to include tap settings of the transformers as decision variables. Now, we're actually not explicitly using this, but this is where we're going to start. And so we're going to have this layout where we minimize system losses such that we observe our regular power flow that we all know and love from 530 and 476. And then we're going to also have the power flow on the secondary side as well as the primary side. And then we're going to restrict the voltage limits because we want plus or minus 5% of 1 per unit. And then we also have tap limits because taps are usually up or down 16 taps. And it's like 0.5% per unit that it changes the voltage. And so this has been done for decades where you model the taps of the transformers as continuous variables and then you round to their nearest discrete value. And there's papers explaining this and why this is actually a good approach. And what we're doing is we're going to cast this OPF as a rank-constrained semi-definite program. Now, in order to do this, we can't explicitly model tap positions like you would normally do. So we have to reformulate our model so that the power transferred through, or what I call around the transformer, is going to be our decision variable. And then once we have our solution, we can go back and actually find what that tap ratio is and what the physical tap setting would be corresponding to that. And so we do this because we want to apply convex solvers, in particular distributed solvers, by leveraging semi-definite programming to tackle the non-convexities of the power flow equations. And so let's kind of go back to basics. We know that power flow can be described as nonlinear equations. We've all seen this expression right here for the power of a particular bus many times. This set HI is the set of buses that are directly connected to bus I by a transmission line. So that's what we're going to sum over. And so what I'm defining here is we consider this W, which is complex. In this case, it's n by n, which is the outer product of the voltages, where those are an n by 1 matrix. And we end up getting this a matrix that has the form here, and it will be rank 1 because it's an outer product. And so what we can do is we can take that power flow equation that we're used to seeing where we had that summation, and we can rewrite it as the trace of the matrix product you see here, whereas this is the power at bus I, this is the power that's transferred through transmission line IK. And so what happens is we end up writing this linearly in terms of W rather than the nonlinear where we have like the B squareds and everything like that. And then this is just how I define HI and AIK, where the EI is essentially like a pointing vector where it's 0 everywhere except for the ith row. Okay, just to give you an idea what this looks like, this is a 2-bus example, single transmission line. We end up having these matrices right here. This is the Y bus. I've already transposed and taken the conjugates. And then what you see here, we end up getting the expressions that we want. Okay, so back to kind of the basics on modeling transformers here. So this expression here, you've seen in 476, you've seen in 530, and this is relating the current that goes into the primary side of the transformer. In this case, my symbol is a voltage regulator, as well as the current, which is, I call it SIST, going into the secondary side. And this is the relationship. And this is really what we're trying to avoid in our formulation, is this 1 over T squared or this 1 over T here, because we want everything linear in W. And so then this expression I put here just to kind of explain this term that we're going to use later on. And so we don't want our transformer to be a phase shifting transformer. So by constraining the voltages on either side in this way, this prevents the phase shifting, and this just ensures that the signs on the primary and secondary side are the same. And so ultimately we can relate that to the off-diagonal entries of that W matrix that I defined on the previous slide. And in this case, because their phases are the same, these entries right here are going to be equal, and they're going to be real because W, the off-diagonals, are conjugates of one another. And so this is how we update our minimization problem. I'm going to use this 3-bus network that was on the previous slide throughout. And so what we do different is we take the transformer, and so we add this virtual secondary bus on the secondary side. And then, like I said, we're going to track the power that goes essentially around the transformer. And so our minimization problem looks like the following. So we're minimizing losses here. This is just the power that's coming from the feeder that minimizes system losses. This is the traditional power flow on every bus except for the primary and secondary sides. This is going to be the power flow on the primary side, where that power that goes around the transformer acts as a load. And then this is the power flow on the secondary side, where that quantity acts as an injection. And then we're going to limit the diagonal entries for the plus or minus 5%, 1 per unit. This is going to be the diagonal entry for that virtual bus on the secondary side relative to the voltage on the primary side. And then obviously we have this condition that was on the previous slide that prevents phase shifting. And this is rank 1. So at this point we don't have a convex problem. And so what we want to do is we relax it so we have a convex problem by...
Maybe you can explain me a little bit better
what all this is right here?
Right, how, because that picture is a little bit misleading, but maybe you can explain a little bit better in the whiteboard that essentially what you're doing is you move with the ideal transformer, and then you have one loading on one side, one on the injection, on the other side injection, that they're the same, all that. So.
Okay, so essentially what we're doing is we're disconnecting the network. So we have two areas. So this would be on the primary side. This would be on the secondary side. And so we would have a load that comes out, and this is that S, what do I call it? PTSD prime. And then we have an injection on this side, which is the same value, only it's technically negative. And then we enforce the voltage on this secondary side relative to here. Because, for example, this is a secondary, this is a virtual bus, right? And so this is the one we want to be plus minus 5%, 1 per unit. And this one we don't really care as long as this one's within the range.
So where do you enforce that, actually? Where is that the enforcement of the...
So the enforcement of the bus that's on the true secondary side, if you want to call it that, is enforced right here because it's just a normal bus, and the virtual bus shows up right here because it's relative. So it's the virtual bus relative to the primary side for the minimum and maximum tap ratios.
So that's essentially the limit for the...
Yeah. So the primary side could be at 1.05 per unit, and the virtual secondary side could be way above 1.05 in that case.
And maybe you can tell what the eta underbar and eta overbar are.
I use these as 0.9 and 1.1.
No, but what they are physically, I'm not sure if they got that they are the limits of the taps.
Yeah, it's the ratio for the taps. So how they correspond. So like, for example, if there's 16 taps up, depending on what it is, I usually use it as 5/8%. And so one tap is 5/8%, and then it ends up being plus minus 10% with the 16 positions.
Okay.
So we relax that problem, so that's convex, by removing that rank 1. Everything's the same except for the rank 1. Now, I'm sure a lot of people haven't looked too much at semi-definite programming, so this is a graphical representation of what is actually going on. And so the way I got these graphs is, this is the power that gets transferred through a transmission line IK. And so this would be the power coming from bus I. This would be the power coming from bus K. And what happens is, if you hold the voltage constant, because what voltage does is, if the voltage is changed, you essentially get like these level sets. So we just hold it constant because we can always grow this ellipse if we wanted. So I put the voltage at 1 per unit, and then I use the phase difference, which is the theta I minus the theta K, as the parametric parameter, and you get this ellipse right here. And so when you have the rank 1, which is that W where it's the outer product, that is the blue line, the blue ellipse. But when we relax it, we allow solutions to fall within the gray area. And so we'll have something larger than rank 1. But what's important about this is that now we have a convex set. And if you look here, and I do this line on purpose because power losses, this is like a thermal loss on a transmission line. The power loss on a line is the sum of PIK and PKI. And that shows up as this line right here, which means that the solutions we actually would want to the convex problem is this red shaded area, which means the actual solution we're interested in is this boundary condition. Now, zero losses falls right about here. So when we have an objective function that's minimizing losses, the objective function comes from the lower left-hand side. And so the solution to the convex and non-convex problem fall on this boundary, and that's why you get a global minimum.
Wait, you said zero losses.
Well, like,
Minimum losses.
yeah, like if our loss was 0 because everything was perfect, it would fall right there. It's because this is like, this is not 0, 0 here. 0, 0 is like right here.
Okay.
Yeah. Yeah, I did it because it would be messier to look at. Now this sounds amazing. Why don't we do this all over the place? Well, the reason why is because it doesn't work everywhere. It only works in specific cases. And this is here just to show you a case that it doesn't work. And this happens mostly with transmission lines when you have congestion, where you, for example, you limit your reactive power because you have to have so much reactive power, or you can have more reactive power, but you can't have 0 reactive power. And so when the voltages are fixed, there's a linear mapping between the reactive power and real power. And so those constraints show up on the real power as the following. And so if we're minimizing from the left, and so we're minimizing over this convex set in the red, and we come and we hit this right here and we choose a solution there, that's not physically meaningful in the rank 1. And so that's why it doesn't always work. So for example, transmission systems, when you have different LMPs, because of congestion, SDP won't work. So this kind of summarizes all of that. So when W is rank 1, then the solution is a global minimum, and it's physically meaningful. We like this because we like doing convex solvers. This does work for single phase tree networks, but the disadvantages is when W is not rank 1, the solution is not physically meaningful. The other thing is, in power systems, it's not fully characterized when this does or doesn't work. We know it works in some mesh networks, doesn't work in others, but we do know it works for tree. And the thing that we're actually really interested in is three-phase tree networks, because we don't necessarily know when it always works for three-phase tree networks, but it generally seems to work experimentally, but we got to actually define when that happens. And so going back to that formulation I showed, the one with all the math, and I actually ran it. And so you're really excited because you got this formulation, you get it back, and you're like, oh, I have a rank 2. That means nothing to me because I wanted rank 1. And so we started looking at what happened. And so if you look at the W that I got from that, and you kind of partition it relative to the transformer. So if you look at the submatrices for this W1 would be on the left there, and the W2 would be the partition on the right. We find that these submatrices are positive semi-definite, and they're both rank 1. The W as a whole is not rank 1, it's rank 2, but it's also positive semi-definite. And so what that did was that led us to the following proposition that shows up in the NAPS paper, that the convex SDP relaxation problem with matrix W can be recast as one involving its 3 submatrices, where we have that W1, the W2, and then we also have this W right here, which is the coupling between the partitions right there. It's not the whole thing, it's just this. And so we minimize our power over that, subject to the original power flow constraints as well as the PSD constraints that I just listed off. And we find that we can actually recover the solution in this method. And the reason why is because each submatrix or partition, the relative phases between the buses that belong to that partition is actually correct. And we just have to correct for the phase difference between the partitions. So we can recursively get the correct answer by starting at the feeder and going downstream. Now, this is great, but the problem is it doesn't work for 3-phase because we lose the information between, because there's about that 120 degrees phase difference between B and C phase relative to A or whatever, and so we can't get that. So it just doesn't work. We got to do something different. And so what we do is we maintain this idea of the power that that goes around the transformer, but rather than disconnecting the graph, we connect it with a resistor. And so that introduces this other power of interest, this ST, which is actually the power that goes through that resistor. And so the reason why we like this is because now the graph is connected, so we can get a W that's rank 1, but we have to be very careful because we want that ST to be 0. We don't want anything other than 0 because otherwise we're not going to get the right answer. The other benefit is because we're not trying to force any sort of phase shifting or anything weird like that, we can drop this constraint that I talked about earlier. Less constraints are always nice. And so I have some case studies that kind of demonstrate applying this method to this 15-bus system, which is derived from the IEEE 13 bus. I added 2 buses between the feeder and the voltage regulator just so that the feeder, the primary side wasn't the slack bus and the only bus in that partition, just because, that's not as interesting. For the single phase results, I used the dominant phase, which was C phase. It's everywhere but 652. And so this is comparing my optimization results. So if I go with that original formulation where I had that ideal transformer, I had a rank 2 matrix, but my submatrices were good. That's this first column here. Now if I reformulate the whole thing where I split it into different partitions and then kind of link the partitions, I get the same answer here. And that was just kind of there for a check. But you can see that I get all the same answers there, which is good. Then the non-ideal case, that's where I added that resistor. You can see across the board, the voltages are the same. The objective function as well as the power that gets kind of routed around the transformer, they're just slightly different, but they're pretty much the same. And really the only difference is that we do have this slight power loss on that resistor, but it's good because it's several orders of magnitude smaller than the power that kind of gets routed around it and through the network itself. So we're very happy with that, and then they all rounded to the same tap position ultimately. So that's single phase. Most distribution systems are not this ideal single phase, so we did the same thing with 3-phase where we have to use the resistor because, like I said, we couldn't recover the solution using the original method. And so this is my answer here. And so I wanted to check this, and so I'm looking at these results, and again, I'm happy because the power in my minimization that gets through that resistor, that it goes through the transformer and versus routed around, there's several order of magnitudes difference. I left the tap positions unrounded just so we can kind of see what the raw answers were. And with this, you get an objective function of 23.48. Now what I did as a check is I went through and I did power flow for every single transformer position because it was a 3-phase transformer. I had a tap for each phase, so I did every combination. And I found that the answer I liked the most, the best answer with minimizing the cost was when the taps were at -9, -11, -10. I can go up and down 16, so that's kind of near their limits, but not quite there. And if you were to round these, you can kind of see I'm already at like -9, -11, and then this -10 is just slightly off. And so that would actually round to -9, -11, -11, but we get the same minimum cost. Now the kind of the differences between those is that's kind of like one of those, I guess you could call it kind of an equilibrium point where it's really, really close. And so the reason why this one is a better answer is because The voltage is a little bit lower here, so it's closer to 1.04, whereas this one's closer to 1.05. And so, kind of wrapping up, we discussed the inclusion of discrete tap positions in the semi-definite program formulation. We talked about the rate condition that we experienced on single phase and kind of how it relates to three phase. And then future work is, again, we're going to be focusing mostly on three phase because that's what people are really interested in. And then we want to apply this to some sort of overall scheme where we're combining fast and slow dynamics. And so with that, are there any questions? Good? I guess that's it. Okay.
Thanks. It's the full screen, yeah.
You can pronounce your last name properly.
Sridharan.
Okay. All right, our second speaker is Srikanthan. Srikant received his master's degree in electrical engineering from the Indian Institute of Technology in Madras. He has worked as a research engineer in Siemens Corporate Technology and later in GE Bangalore. Currently, he is a PhD candidate working under Professor Krein in the area of motor drives.
Thanks, Samay. This is a presentation on the system level loss optimization for induction motor drives, and I've made this presentation really high level so that everybody can understand to some extent, because not everybody here works on machines and drives. So even the slides are minimal too. So going ahead, this would be the presentation outline. First is the background to induction motor drive loss optimization problem. This is pretty much well motivated because you can start with a well-known classical statement that induction motors are the workhorse of the industry. They consume about 2/3 of the power and so on and so forth. So the motivation is already there. So we won't spend a lot of time on that. But then we would move on to what is called as a duality-based control for voltage source inverter and current source inverter topologies. So induction motor is an AC motor. So obviously we need an AC input to the machine terminals. So voltage source inverter and current source inverters are the primary configurations by which you can convert DC power to AC power. And then moving ahead, we look at the development of field-oriented control, which is a kind of a vector-based control for AC machines. And this is modified a little bit because of the presence of output filters, which we'll see later. And finally, this is the crux of the entire story. We would compare the system versus machine-based optimization results. So the need for drive optimization is clearly known, because a drive is nothing but a combination of all these factors. We have the AC motor, we have the filter, the inverter, and the DC link. But when we look at the literature, predominantly machine optimization is what is being done, which means that this induction motor has been optimized for efficiency or minimum losses. But obviously, just minimization of the machine alone is not going to give a global optimality or the drive optimality in this case. And that's the reason why we want to study, is there any benefit or advantages to do a system level optimization of the entire drive system, which is a combination of all these components. And then it's obvious that the overall efficiency would depend on the efficiency of not just the motor, but the filter as well, because of the reason that there are equivalent series resistances in the L filter and the C filter. So obviously the filter is also subject to losses, which we need to study. The inverter, we know that they are subjected to the switching losses and conduction losses, and that also is a substantial portion of the entire drivetrain losses. And this, of course, has been a neglected child for many decades, because of the fact that DC link was always assumed to be lossless, but this is not really true. Especially in the cases when DC link is current source driven and not voltage source driven, a good percentage of losses is happening in the input side, which people tend to neglect. So our objective in this work is to combine the loss minimization along with the control. The control of the motor, which we would look at as a vector method or field oriented control. So we combine both these objectives together. So moving ahead, we want to generalize this to any kind of a drive problem, specifically for induction motors, but it could be driven by a current source inverter, CSI, or a voltage source inverter, VSI. And there is a major misconception or a myth in the literature that CSIs are not as efficient as the VSIs. And this is not really true. Of course, it can be true depending on the power levels, but one cannot really generalize that CSIs are subject to more losses than the VSI because of the classical argument of duality. Whatever was possible with a voltage source inverter should definitely be possible with the current source inverter. Even there is a topological duality, which means that this configuration can be obtained from this and vice versa. And there is also a control duality. In this slide, we look at the physical or the configuration duality. In voltage source inverters, the input, as the name indicates, it's a voltage source of value VDC. The inverter has 6 switches. So the same 6 switches are present in the current source inverters. In the VSI, we have anti-parallel diodes, because just in case there are inductive loads, which a machine obviously is, we need current to flow through this freewheeling path. But in the case of a VSI, we cannot turn on both switches of the same leg together because of the obvious reason that it's a short across the DC. That's to be avoided. But in the case of CSI, this is a valid state, which means that I can turn on both these switches together because the input side current is regulated, so there is no such thing as short circuit. But then we cannot open the current, because this is a current source. You cannot afford to have an open path in any of this electrical circuit. So which means that I need to ensure that at least one switch from the top side and one switch from the bottom side should be turned on at any instant of time. So these are the necessary conditions. But apart from that, there are certain other dualities which we will not talk about. But in order to establish this duality and give a formal notion of how this duality is done, we look at the space vector map. It is not complicated. The space vector map is nothing but a map of the switching states. For example, what does this indicate? These are hexagons in nature. So let's say we have a state 1, 0, 0. It just means that a 1 on A phase represents the top switch is on, and a 0 in any phase indicates the bottom switch is on. So a state of 1, 0, 0 means the top switch is on in A phase and the bottom 2 switches are on in B and C phases. So this gives rise to a voltage vector, which is V1. And this procedure can be repeated for all the possible states, and you arrive at this space vector map. And by duality is not something we impose, it is inherently there. It's by nature of the construction of voltage source and current source. And so when we look at the duality, it is just the same hexagon, except for the fact being that this looks a little tilted. In fact, it's a 60-degree 30-degree phase displacement of this hexagon results in this hexagon. So whatever was possible with the voltage source inverter should definitely be possible with the current source inverter. But if you look at literature, all the comparisons that have been made are really unfair, because of the reason that VSIs are always operated by high frequency PWM, but CSIs are projected to be low frequency PWM, which need not be the case, because IGBTs are devices which can switch pretty much at high frequencies, and whatever was possible as a PWM technique with VSI is possible for CSI. And so now that we have a common comparison or common standard for comparison of the true drives, we can compare them really one-on-one. But this slide is not to indicate that both VSI and CSI are same. There are differences, there are reliability issues, But that needs a different investigation, and one should not be prematurely conclusive about saying that VSIs are better than CSI. That's the point that I wanted to make. So how do we go about the translation? Now, well established current methods or voltage or current control techniques are available for VSI, but we need to convert them to equivalent techniques in to CSI. And what we do is make use of the space vector map again. So let us say there was a state 100 that corresponds to a state of, let us say, 61 on the CSI. So just you can think of it as a digital design system, and then you just convert logic from one system to another. So when these states, or let us say these switches were turned on in CSI, so in VSI, the corresponding states in CSI will be 4 and 5. So it's just the switching map. It's not really complicated. Just a set of switches were turned on in VSI, another set of switches are turned on in CSI, and what is the relation? That's what we study through this Boolean logic table. And once we form this table, it's easy to derive the Boolean expressions by whatever method. The simplest one is Quine-McCliskey method and so on. So you can derive this kind of a logic map. Now what does this say? I have a switching signal for VSI, but I don't have to independently develop a technique for CSI. Rather, I can use this logic map to convert switching signals from VSI to CSI. So the user really does not have to bother about whether it's a VSI or a CSI to develop an independent current control or voltage control technique. Rather, the space vector map or the translation map could be used to generate the corresponding switching signals. So now this is established. We had the inverter, and we had the DC link, and we had the motor. But now the current control or the voltage control technique for the inverter is fixed. Now let's go to the motor control. So what we do in this case is a field oriented control. It is a classical vector control method. Now what do we mean by that? A DC motor is relatively very simple to operate in terms of speed control, because of the reason that especially in separately excited motor, that is what I mean, because the flux and the torque loops are independent. So in fact you can control the flux independently and torque independently. So that gives a good amount of flexibility to control the two loops. But in the case of AC machines, let's say induction machines, the excitation is only one. You have a 3-phase AC supply, but you do not have a control over controlling flux and torque independently. But now there is a transformation which is called as a Park transformation. So this is people who are doing 568 now may be aware of this. So what we are doing through this transformation is break down the AC machine and look at it in a sense as a DC machine. It is exactly not so, but to understand we can say that the AC machine is kind of made to emulate a DC machine. So when it becomes a DC machine, both the flux loops and the torque loops can be controlled independently. So this is the diagram that can be helpful in understanding this. Let's say we map all the vectors on the phase plane. So there is a stator frame which is fixed, but then there is a rotor which keeps moving at the frequency which is decided by the torque and the frequency and so on. But there is also a rotor flux vector. The input voltages are given, and that generates a stator flux, and the stator flux interacts with the rotor, and then the rotor currents are available, and the rotor currents will produce rotor flux. This is a typical interaction in an induction machine, but assume that the rotor flux is given like this. So we need two axes to represent this vector. So we make use of the orthogonal transformation here. So there is a q axis and a d axis. So what we do by this control method is superimpose the rotor flux vector on the d axis. So let's say there was a vector lambda r, its horizontal component would be lambda dr along the d axis given here, and there is a q component on the q axis. So if you superimpose the lambda r vector on the d axis, the quadrature component becomes 0. So that's the advantage that we get during doing this control. So the torque equation, the conventional regular torque equation is given like this. But using this control, what we've made is we've made the q component to be 0, and now the torque equation becomes like this, and the flux equation becomes this. So you can see that the flux can be changed by IDS component of the stator current, and the torque can be controlled by the IQS component, assuming that you fix lambda r at a constant value. But this is not the end of the story, because it's a fact that you can change the value of rotor flux in a machine and then obtain minimum losses. This is called as loss minimization through rotor flux control. So it's a standard result. So available, you can look at any textbook that talks about machine loss optimization. So there is a certain value of rotor flux that results in the minimum losses in the drive, but this is all done for the machine, as I was talking about earlier. So the green line is what I am talking about. Let's say that we know only machine loss right now. The machine loss curve is given like this. So you can see that the machine loss becomes minimal at let's say 0.42 volt second of rotor flux. So it is minimal. So it is generally recommended that you operate your machine in such a way that the rotor flux is 0.42 volt seconds. But that is not really true, because that results only in the minimum machine loss. But when we integrate all losses, for example, I've just added the DC link loss. So the DC link loss curve is given like this. So it needs, when there is more flux that is given to the machine, the DC link losses become lower. That you can look at through the machine equations. So, but now the total loss of the system becomes like this. So if we are really interested in finding the true optimal point of the losses in the machine, then we have to study the total losses and not the machine losses. So when we add all the losses, we see that the minimum point goes here. So assuming that the system was earlier operated for lower machine losses, the optimal point would have been here, which would have resulted in increased total losses of the system, which we don't want to do. So now the crux of the story is that we need to ensure that the command flux for the rotor should be at this point and not at this point. Now we've seen the control for the inverter and control for the motor, but there is a classical method of what is called as a maximum torque per stator ampere control. But now this was done with the machine and just the inverter, but not without the filters. But now when we introduce filters into the system, the story is a little different, because the maximum torque per stator ampere gets converted to another technique which we can evolve as a minimum inverted DC bus. Now, in other words, we have this filter. So let us not look at the filter just as a harmonic mitigator, because generally in most of the drives we look at filters as components to remove or eliminate harmonic components. But this can also be seen as a provider of the magnetization current for the induction motor. In other words, we can also say that the reactive power of the induction motor can be supplied by the shunt capacitors. So which means that the inverter current would be minimum, because of the reason that the reactive current is supplied by the capacitors. And so the entire system, which is the induction motor with the filter, will not draw any reactive current from the inverter. So the inverter current becomes optimal. But what does this have to do with the bigger picture of the losses minimization, the entire drivetrain? It is just the inverter losses will become minimal. You can see from this curve that the maximum torque per ampere demands this kind of a DC bus current. But when we introduce the filters and then do this procedure, we see that a lower current is needed for the DC to be drawn from the DC bus, which means the inverter and the DC bus losses will be lower than what was expected for just the machine optimization. And let us not look at this. This may be a little confusing right now. So going on to the evolution of the minimum inverter DC bus ampere, we can also look at it in one more way. This maximum torque per stator ampere can be recast into constant torque angle control, which was one of the theses done in the power group. So this says that in order for torque to be maximum, your torque angle, which is the ratio, the tan inverse of IQS over IDS, has to be 45, and that's straightforward when you do the math behind it. So this is 45, but when we introduce the capacitance or the filter structure in general, we can look at this problem as a variable torque angle control. So that's just to this slide is just to look at the inverter current control from a different perspective. Yeah. Yeah.
Can you go back to the previous slide?
Yeah.
And so, this is what we're talking about, is what we're ultimately trying to optimize with
Yes.
the system.
Right.
And so go to the next slide. I understand what the motor is, So what is the other component? Is it just this, or is it all of this?
All of them.
So all of this,
Yes.
go back to the previous slide,
Yes.
is this is the motor, and
Yeah.
this is the drivetrain.
That's right.
This is the total.
Yeah, in fact, this is taken, this is a combination of just the DC link and machine losses, just to drive the point that even if you add any other loss, the optimal point is going to shift. But when you add all the losses together, the difference is quite huge.
So from a terminology standpoint, when we say DC link loss,
Yeah.
that's from the DC source to the terminals of the machine.
No, it's just the DC link. This curve should have been the total losses, which is DC link loss plus inverter, but that I have not included here.
So on the next slide.
Yeah.
So the DC link is
Here. Yes.
So all of this is part of the motor?
No, this curve does not have all the losses.
Oh.
So the total loss is a little misleading. I knew I was wrong here. The total loss is just the combination of the DC link and machine. This is just to drive the point that even if you add one extra loss, the optimal point is going to shift. So when you add all the losses, which is DC link, the inverter, and the filter losses, you could see a tremendous shift in the optimality value. So
that leads to the question is, what parameters are you trying to vary to reach the optimal point? Because I can see you're trying to change machine geometries, or you could be trying to optimize the switching machine.
Okay, this optimization is done for using the control parameter, which is the rotor flux and the capacitance value. So we have, the user has, let us say that there are, the rotor flux is one of the, which is classical control method of machine loss optimization. But we can also choose the value of capacitance in such a way that you supply a certain amount of reactive current needed by the motor. So now the user has two values that he can choose from, or rather 2 degrees of freedom. One is the capacitance value and one is the rotor flux.
Rotor flux and dial you can turn.
Huh?
The rotor flux and dial you can turn.
No, you will have to command it through, let us say, a reference value. When you can, how do I say that? Okay, there is, let's say there is a certain command for rotor flux, and that indirectly gets translated to current command. So that's what we do here. So once we derive what is the optimal value of rotor flux and the optimal value of capacitance, then we go about designing the control loop for the inverter. And so now the total losses, we can see in the next few slides, the total losses become lower, but how much will be the question that needs to be addressed. So how do we go about formulating the objective function? This is all offline optimization. This is not an online optimization, by which I mean that you don't have to really run it when the system is running, because since we assume that the system parameters are well characterized, for example, you know the system very well, the machine inductance, the magnetizing inductance value, the rotor resistance, the stator resistance, and the conduction losses and switching losses. Let's assume that they are characterized to sufficient degree of accuracy. And so you formulate your objective function as a combination of all these losses. And the user is also given the flexibility to have greater weight on any of these losses. So if I equate all the other constants, the k constants to be 0, preserving just k1, it becomes the classical machine optimization which has been done in the literature. But now there are constraints which we have to enforce. The optimal value should be less than saturation, which is quite obvious. We cannot run the machine beyond the saturation limit. And there is also a thermal limit, because when you decrease the rotor flux below a certain point, the IQ component of current has to jack up in order to support a certain torque, which means that the system would, or the machine would start heating up, which we want to avoid. So we have to ensure both the lower limit for the flux and the upper limit for the flux, which is saturation. And this has also been grossly neglected in many papers. So once this is set up, now we run this optimization problem just as a grid search. We don't have to use any sophisticated techniques to do the control or optimize the objective function here. Just use the values that are possible for rotor flux. Let's say you command 0.2 volts second to 1.1, let us say, which is a saturation limit, and the capacitance value, let's say 5 microfarad to 50 microfarad, whatever, depending on what is the size consideration and how much capacitance can be provided from the external world and so on. So these are some of the physical constraints. So assuming that they have all been dumped into this function, we can generate what is the optimal value of rotor flux and capacitance at each operating point. By operating point, I mean that a frequency of operation, because for every frequency, let's say you run this optimization procedure for 10 Hertz to 60 Hertz, you get different values of rotor flux, you get different values of the capacitance as well. So once you combine all your results running this algorithm right from 1 Hertz to 60 Hertz, you can generate a graph, you can generate all graphs like this. So this is just to show how the loss surface looks. The loss surface thankfully does not have any discontinuities because of the reason that the functions are very smooth. All the functions that have been, all models rather that have been used for objective function are all very smooth, and so we get a unimodal point, which means that we are definitely able to find a point where we see that the losses are optimum. Yeah. This is 5 HP. Yes, it's a 5 HP machine. So if you choose a wrong value of the rotor flux or the capacitance, the losses can be substantial. They can be close to 50-60%. So, but once we repeat this optimization for all frequencies, this is the graph that we get. This is probably, you can say, the final result of all I was talking about. So the rotor flux profile for the earlier case of just minimizing the machine alone would result in a curve like this. But when we do a system-based minimization, the rotor flux that has to be commanded for each of these frequencies. For example, if you want to run your machine at 60 Hertz, this should be the flux that you have to command and not this one. And now you also see the how much of loss reduction that you get. If you do a machine-based minimization, which is the green curve, you see that compared to a system-based minimization, we obviously get a good amount of loss reduction when you do a combined system-based minimization. So this is the major point that I wanted to talk about. So now some of the major conclusions is that the first few slides we saw why CSI should not be treated the way they are, that they are not low frequency inverters, line frequency inverters. They can be potentially used at high switching frequencies. And how do we go about designing the current control method is just by transferring the VSI control technique to CSI control technique by duality. And then we see that system level loss minimization is what we have to attempt when we have to look at loss optimization as a total drivetrain. And this by repeated simulations you can see that for different loading conditions, if the machine is fully loaded, the advantages are not quite too huge as compared to system based versus the machine based. But when you don't load the system to its maximum capability, let's say you load it at 60%, 50% of rated conditions, then system optimization is going to give really a good amount of improved efficiency. And system level loss minimization can also be interpreted as a variable torque angle control, because we've also seen literature which talks about constant torque angle control, which need not be the case. So you can actually vary the torque angle also and then see that you can ensure minimum losses in the drive. So acknowledgements to Geiger Center and Rolls-Royce who have sponsored this work, and thanks for your attention. I can take any questions that you have. Yeah.
During the capacitance of the transceiver to achieve optimization, how does it affect the harmonic multiplication capacity of the system?
Yes. So in this case of let's look at this. So when we enforce this, the value of capacitance itself is enforced in the objective function, because if you don't use the required value of capacitance, the harmonic can be quite high. So the THDs can be quite high if you use a low value of capacitance. So by repeated simulations, what we do is you say that, okay, if you go below a certain value of capacitance, your THD goes below 5%, which is not correct, and you don't want to go above a certain value of capacitance as well, because size becomes huge. So it's a trade-off. So in this objective function, we have converted the THD into the minimum capacitance value, so that in this case, when you use a capacitance more than 5 microfarad, you see that the THT is below 5%. So, and when you go above 50 microfarads, you see the size becomes quite huge. And so we want to restrict this capacitance value and insert that into this objective function. And then the loss minimization is done. So that's one way of tackling that problem. Okay, if we don't have further questions, yeah.
Let's give some context on when you see the CSI versus CSI.
Okay. When we look at the literature, there is a huge bias towards VSI, especially in the applications that we are talking about. Let us say 10 HP, 20 HP. But when you go to the megawatt size range, like as in the cranes and heavy duty equipments, then CSIs become really favorable. That the one reason why VSI is favorable is because of the fast transient response that is possible with the voltage. But in CSI, there is a huge inductor sitting here. So the transient response is definitely limited in the case of CSI, but that should not be a limiting factor when we consider the efficiency aspect. But there is another caveat, because CSIs are much more reliable than the VSI, because it is a known obvious fact that the capacitors are not, the reliability of the inductors are quite huge than that of the capacitors. So this definitely, as a drive that has to last for a long period of time, then CSIs become favorable because of the reliability factor. But still, this needs rigorous analysis. So one of my future work is possibly to integrate the reliability also into the cost function and see if what the literature says, if it's really true or not. Because there is, it seems to be open that there is no real quantitative conclusions about which should be preferred under which circumstances and what is the power range that defines this clear difference of using a VSI and CSI. But the duality still exists, as we say. So whatever we are able to achieve with CSI should be possible with CSI, of course, with the other things considering. So yeah, I think with this I conclude my presentation, and thanks for your attention. How does, oh yeah.